The SpikePuter modules are now complete. We've got the register memory here, the arithmetic logic unit or ALU here, and then on this pegboard there's control logic, RAM and ROM, the clock chip, and the program counter. And now that we have all of these made with some rather nasty looking cabling right now, and obviously this will get cleaned up considerably later when this third pegboard is mounted on the wall, we can actually start writing programs and executing them. And to do that, we use the SpikePuter's direct memory access model and my other computers. So I was able to write a quick program with 3 different modules. One to do a counting and memory test, one to calculate Fibonacci numbers, and one to do a quick animation using the LEDs on the register memory. And I programmed that in the SpikePuter's machine language, and then I compiled that with a compiler that I wrote on the Macintosh, and then with the data from the compiler, I pasted that into a program that I wrote to load up an Arduino card with that data, and then when the Arduino card runs, it stops the SpikePuter through that direct memory access model and writes the program into the SpikePuter's memory. Then once we do that, we can actually execute the program. So let's give that a try. First we turn on the SpikePuter, and I've already loaded the program memory onto this little Arduino card here. So we turn that on, the memory's just scrambled. If I reset the Arduino, it will upload the program, and the program is written such that it looks at the general purpose input first to figure out which of those 3 programs to run. So I'm going to set it at 0 right now and push reset, and 0 is the program to increment and count and test the memory. So what it's doing now is it's clearing out the registers now that it's figured out that it wants to run program 0. And in register 1 here is the numbers that it will be sequencing. Register 2 is the memory address where it will be storing that. And so the program increments register 1, stores it in the memory location pointed to by register 2, reads back register 2 to make sure that the number was written correctly, and then repeats. And you can see it's going pretty slowly now because we're at a fairly slow speed setting on the SpikePuter, but you can speed it up by just switching this little variable resistor here, and I'll switch it to the maximum that the SpikePuter can run. You can see it actually can count pretty well. This is on the order of 7,000 hertz that it's running at right now. So I'll slow it back down again. You can see that it's counting in binary. And the next program we'll run is the program to calculate Fibonacci numbers. So I set the input here to number 1. And when I push reset, it will start at the beginning again, which is looking at the input, seeing that it's a number 1, and it'll start calculating Fibonacci numbers. So we'll give that a go. And as before, it clears out all the registers. And now register 0 here is keeping track of which Fibonacci number we're on right now. Registers 1 and 2 represent the previous 2 values of the Fibonacci sequence, and register 3 is the actual Fibonacci number that it's calculated. So as you see, right now we've got 1 plus 1 is 2. Now 1 plus 2 will be 3. Then it moves the numbers up. 2 plus 3 will be 5. Great. And moves them up. 3 plus 5 is 8. And there we go. And we can speed that up a little bit too, and it's going to go through all of the Fibonacci numbers until it runs out of space, which is 16 bits. And that final number, go even a little bit faster. Well, once it figures out all the numbers, the final number is B520, by the way. It's the largest Fibonacci sequence that can be stored in 16 bits. When it's done with that, it then recapitulates the first numbers of the sequence. 1, 2, 3, 5, 8, and 5 plus 8 is 13. So that works. Now let's do a fun little animation. That's program number 2. And again, reset. And I don't know if you could quite see the ghost in the machine here. I'll speed it up a little bit. Voila! 3 SpikePuter programs running on a fully functional SpikePuter CPU.